The second property of groups that comes in really handy is described in Theorem 2.2, and it has to do with cancellation. And we use this a lot when we work with real numbers all the time. So imagine you have an equation that's 2x is equal to 2y. Then for years now, you always just say, well, if 2x is equal to 2y, then x is equal to y. Why does that work? Why can we do that? Do you ever stop and think about why that's true? Well, really what we are doing is, when we're working with real numbers, we're dividing by 2, or in the language of our groups now, we are multiplying by the inverse of 2. And that is why this cancellation works. It has something to do with inverses. In groups, we have cancellation as well, and since not all groups are commutative, we have actually right and left cancellation. We have to consider them separately. So the first equation right here says that if b times a is equal to c times a, then b is equal to c. And so this is the a is on the right, and we get rid of it. So this is right cancellation. And it also works from the other side. So if you have AB is equal to AC, then the A right here is on the left and it disappears. We just have B is equal to C, that is left cancellation. And so in a group, you can do that. If BA is equal to CA, then B has to be equal to C. And if AB is equal to AC, then B has to be equal to C. And as I said, this has something to do with the existence of inverses. So let's prove this. Let's take any group elements A, B, and C that are in G, and we need an inverse. And which inverse do we need? Well, it's the inverse of the element that is disappearing. So let A prime be an inverse of A. Okay, then what do we have? Let's look at part I, little I. We have BA is equal to CA. That's what we're starting with. And taking the inverse of A from the right, so looking at BA A prime, doing that to both sides, we have BA A prime is equal to C A A prime. And since A is the inverse of A prime, or rather A prime is the inverse of A, this gives us just the identity element, and A prime on the right as well. That is also the identity element. So what we have is B times the identity is equal to C times the identity, but multiplying or composing or whatever our operation is operating by the identity just gives us the element itself. So we have B is equal to C. And that is what we wanted to conclude. So it's a super short proof. Part I is very similar, and you try it.